So we can look at the second stage of respiration, and that is the Krebs cycle. Sometimes you can call it the citric acid cycle or the tricarboxylic acid cycle. Tri means three, tricarbon, three carbons, and it is a cycle which is moving around and then repeating itself. So it is not moving in a single direction, unlike in glycolysis whereby we're just having a single direction whereby the 6 carbon atom formed the 2 pyruvate molecules, of which something was irreversible. Now in the cycle we see that where we started from we can end there still at the same time. So the cycle, but of course in this cycle we shall have still some ATP being generated, we shall have NAD and some other molecules which we are going to see in the nearby future. So we realize that in glycolysis, uh, uh, it is the first stage. It is the first stage of respiration, and then we looked at whatever is being involved, and we are going to see what is involved in the Krebs cycle. So first of all, we can see that by definition, Krebs cycle is the series of enzyme-controlled reactions which occurs in the mitochondrial matrix. So the site for the occurrence of the Krebs cycle is the mitochondrial matrix. Of course, the mitochondria is only going to be found in eukaryotic cells. Eukaryotic cells have membrane-bound organelles. So eukaryotic cells, and in the cytoplasm for prokaryotic cells, remember prokaryotic cells, they don't have a mitochondria, they don't have a nucleus. So for them, they just have no membrane-bound organelles. So their contents are just dispersed within the cell, so we don't have any compartments or membrane-bound organelles. So instead, the Krebs cycle will just occur within the cytoplasm. So what is being involved is acetyl coenzyme A is completely oxidized to carbon dioxide, releasing reduced coenzymes and then ATP, as we are going to see in the steps. So what initiates our Krebs cycle is this. So this is the first initiation of the Krebs cycle. Before we look at the major steps from step number 1 up to step number 8, we look at a pre-stage, or before entering into the major stages, what takes place. The transition stage from the glycolysis stage to the Krebs cycle. So the transition is always occurring from here, whereby we know very well that the end product of the glycolysis was a pyruvate, and remember there were 2 molecules. So it means that if there were 2 molecules, even in these stages, you're going to be having two molecules taking part in the reaction. That's why in each and every molecule we are going to be having here at the end, we are going to be doubling into 2 because this stage is going to be occurring twice. So remember, there are 2 pyruvate molecules which were produced from glycolysis. So the transition stage from glycolysis to Krebs cycle is just, this is a brief stage which is going to be taking place. And how does it take place? We're having a pyruvate molecule which is 3 carbon atom. 3 carbon atom, remember, 2 pyruvate molecules were formed. Each molecule had 3 carbon atom. So in total, we'll give 6 carbon atoms in the 2 pyruvate molecules. So it is converted to acetyl coenzyme A. Acetyl coenzyme A has 2 carbon atoms, of which if there are 2 carbon atoms, it means that decarboxylation occurred from 3 carbon atoms to 2 carbon atoms. Decarboxylation, how did it occur? We're going to see in the equation. So this releases carbon dioxide and then produces reduced NAD. Reduced NAD is the NAD which is having hydrogen. So someone may be wondering, where does acetyl come from? Where does the coenzyme come from? The acetyl comes from the decarboxylation of the pyruvate. So once carbon and then 2 oxygen molecules are lost, two oxygen atoms are lost, then you're going to just remain the acetyl group, and that acetyl group is going to combine with the coenzyme A. Coenzyme A, where does it come from? It is already coming from the cell itself. The cell has this component, and what is its relevance? The relevance of coenzyme A is to activate the acetyl group so that it can be highly unstable, hence highly reactive. So at this stage, the reaction, the overall reaction for the transition stage is going to be shown like this. The pyruvate is decarboxylated to release carbon dioxide at that stage. We're going to be having coenzyme A coming from the cell, combines with the acetyl group, form acetyl coenzyme A. But before the acetyl coenzyme A is formed, the NAD, which is oxidized, is reduced to NADH, so which is reduced to NAD. So it means that oxidation of the pyruvate occurs at the same time. So there is oxidation and then decarboxylation taking place at the same time. What is being oxidated? It is the pyruvate being oxidized by the oxidized NAD, and oxidized NAD is reduced to NAD. So it means that this oxidized NAD picks up a hydrogen from the pyruvate to form reduced NAD. That's why we are having NAD as one of the products in the transition stage. So acetyl coenzyme A is formed. The acetyl coenzyme A is a highly reactive molecule due to the presence of the coenzyme A. So we can begin with the step number one. Step number one, that is the condensation reaction. The condensation reaction, of course, we know there is loss of water. Of course, we shall see in the summary of the reaction, there is loss of water. At this stage, you're having the acetyl coenzyme A from the transition stage combining with oxaloacetate, which is a 4-carbon molecule. Acetyl coenzyme is a 2-carbon molecule coming from the transition stage, combined with a 4-carbon molecule, that is oxaloacetate, to form a citrate. In other sources, you will find them calling this citric acid or oxaloacetic acid. So it is all the same. Just because the only difference is that the citrate is an anion of the acid, that is citric acid. Just like you can see sulfuric acid. We can also say that the anion of sulfuric acid is a sulfate. So when I say a sulfate, still it can still remain normal. So if you use citric acid or oxaloacetic acid, it is 100% correct. For example, isocitrate, you can also use isocitric acid. Alpha ketoglutarate, you can also say alpha ketoglutaric acid. Succinate, succinic acid. Fumarate, fumaric acid. It is. So that is the first stage, condensation stage. We're having the acetyl coenzyme A, which is a 2-carbon molecule, combining with oxaloacetate, which is a 4-carbon molecule, forming citric acid or a citrate. So in that case, we are having loss. We are having loss of coenzyme A. Coenzyme A is lost at that stage because in the citrate we don't have coenzyme A. Coenzyme A is already lost, and we still have loss of water molecule. Loss of water at that stage because it is a condensation reaction. So we can go to stage number 2. Stage number 2, it involves isomerization. Isomerization, there is rearrangement of the structure whereby the molecular formula will remain the same, but the structure formula changes. So citric acid or the citrate rearranges to form isocitrate. It rearranges to form the isocitrate. So stage number 3, that is the first decarboxylation. The first decarboxylation means that we are removing a carbon atom, or we are removing carbon at that stage. So decarboxylation. So it means that if we're having the isocitrate, because you know the isocitrate is still having 6 carbon atoms. Remember, we are just having isomerization taking place here. So the citrate was 6 carbon. So it means that if isomerization takes place, the 6 carbons are going to still remain. So in the third stage, you're having first decarboxylation. So we are reducing the number of carbon atoms. We're reducing the number of carbon atoms. In that case, when decarboxylation takes place, we're going to have a loss of carbon dioxide molecule at that stage. And decarboxylation is going to be followed by oxidation. Oxidation at that stage, whereby in case we're having oxidized NAD and reduced NAD. Remember, this oxidized NAD is going to pick up a hydrogen from our isocitrate. So it means that when hydrogen is lost, that is still oxidation. So oxidation occurs at the same time, and decarboxylation occurs at the same time in stage number 3, because we're having reduced NAD being produced. Reduced NAD, it has taken away hydrogen. It means it has oxidized the isocitrate. As well, we have had a decarboxylation taking place. That is the loss of carbon dioxide. And then what are we going to form? We are going to form alpha ketoglutarate, or sometimes you can call it alpha ketoglutaric acid. So in stage number 4, the alpha ketoglutaric acid, which we had initially, it was 5 carbon molecule. It was a 5 carbon molecule. So we can call it 5 carbon molecule. So again, we are going to have a second successive decarboxylation taking place. So it means that if we had alpha ketoglutarate, which was having 5 carbon molecules, at this stage when we have the second decarboxylation, it means that the 5 carbon atoms are going to reduce to 4. So alpha ketoglutarate is going to lose carbon dioxide. So it means the decarboxylation has taken place. Another NADH, reduced NAD, is also formed. It means that still there is successive oxidation. It means that in the alpha ketoglutarate there is a hydrogen which was removed. So that oxidation takes place to form succinyl coenzyme A. Now, where did the coenzyme A come from? We said that coenzyme A is already available within the cell. So we don't have that it is formed from this reaction. It is already available. But what is its role? The succinyl alone is highly stable. So it means that it is less reactive. So the coenzyme A combines with the succinyl to make it highly unstable. And the succinyl coenzyme A has 4 carbon atoms. So we enter stage number 5. Stage number 5, we're having substrate level phosphorylation. Substrate level phosphorylation, it means that we are succinyl coenzyme is converted into a succinate. It is converted into a succinate. ATP or GTP is produced directly. So it means that we are having, at that stage, we're having a ATP gaining or GTP gaining a phosphate molecule to produce ATP. So we're having GDP guanine diphosphate picking up a molecule, a phosphate molecule, to form it. So energy is released at that stage, at substrate level phosphorylation. So in stage number 6, we're having oxidation. Oxidation, the succinate is oxidized to form a fumarate. The fumarate, you can also call it for fumaric acid. So oxidation takes place. What oxidizes at that stage? The oxidizing agent is going to be FAD. So FAD is going to pick up oxygen from the succinate to form a reduced FAD. FAD at that stage is used instead of the NAD. So we are seeing that we are having a reduced FAD formed here at that stage. Remember, as the oxidation is taking place, 2 succinate molecules are oxidized to form 2 fumarate molecules. Why? Because 2 pyruvate molecules were formed from glycolysis. So we are going to have each stage occurring in a double wave. So the 7th stage, we're having what we call hydration. Hydration, we are adding water. So hydration, the fumarate is converted into malate. So it means that here in this stage, we are adding water. So in stage number 8, we're having the final oxidation. The fine oxidation. What is, of course, we know the oxidizing agents. We have FAD with the plus, and then NAD with the plus. Those are the common oxidizing agents we are going to be using. So in the final stage, that is oxidation stage, we have the malate being oxidized to form oxaloacetic acid or the oxaloacetate, of which the oxaloacetate is again going to allow the cycle to continue because the cycle is repetitive. Remember, in the initial stages or in the first stage, we had oxaloacetate getting involved. So it means even at the last stage, we must have oxaloacetate being regenerated so that the cycle can continue. So in the second, in part 2, in the second stage, or in part 2 of Krebs cycle, where I'm giving when I'm giving the summary, I'm going to give just the real cycle, of which is going to bring out these real stages. So if we look at the pyruvate, we have a pyruvate molecule coming from glycolysis. Normally, we formed 2 pyruvate molecules, and it implies that the 2 pyruvate molecules are going to be forming 2 cycles. So it means that the single cycle we are seeing here, whatever molecule we are obtaining or we are using, for us to come up with the real quantity of whatever is being formed, whatever is being used, we must multiply by 2, because the pyruvate molecule from glycolysis, they are always 2 molecules. So before we enter into the tricarboxylic cycle, the Krebs cycle, we have what we call the transition stage. The transition stage is like the other stage where we are preparing our glucose into the energy extraction phase. Even here we have the preparation stage. We are preparing our molecule. We are preparing our molecule to enter into the cycle. So how do we prepare our molecule? We must make it highly unstable or highly reactive, like we did for the glucose molecule by adding a phosphate group to it. So we made it highly reactive or highly unstable. So even here, for us to enter into the cycle, we must first make sure that our pyruvate molecule is converted into a very reactive molecule or a very unstable molecule. So what takes place is always a transition stage. That transition stage is the stage which is leading us into the cycle. So what really happens is this. So we're going to have what we call decarboxylation of the pyruvate. Decarboxylation, we are losing a carbon dioxide molecule. So since we are losing a single carbon dioxide molecule from a single pyruvate, it means that for the 2 pyruvate molecules, we are going to be losing 2 carbon dioxide molecules. Then at this stage, after decarboxylation of the pyruvate, it implies that the pyruvate, which was originally having 3 carbon atoms, they are going to reduce to 2 carbon atoms, as we are saying. So in the process of decarboxylation, we are converting the pyruvate into an acetyl group. That acetyl group, we are going to add a coenzyme A to it. Where does that coenzyme A come from? Coenzyme A comes from the cytoplasm, or it comes from the matrix itself, the mitochondrial matrix itself, because we know very well that the Krebs cycle occurs in the mitochondrial matrix, so it is readily available. So the coenzyme A, what is its role? The role of coenzyme A is to make sure that the acetyl group is highly unstable or highly reactive, so that it can enter into the cycle. So at this stage, still we have reduction taking place. We're having oxidation taking place, because we are removing the hydrogen from the pyruvate by using oxidized NAD to form reduced NAD. So this oxidized NAD lacks a hydrogen, and when it has a hydrogen, that is reduction. Remember, reduction can be addition of hydrogen or addition of oxygen. It can also be oxidation. Oxidation can also be loss of electrons, and reduction can be gain of electrons. So our NAD, which is positively charged, oxidizes the pyruvate to the acetyl group, of which, in combination with the coenzyme A, which is making it highly active or highly reactive, we form acetyl coenzyme, of which acetyl coenzyme A is a 2 carbon molecule. So what takes place at in the first stage, because we are dividing our stages into 8 different stages in the cycle. whereby this cycle here, we whichever stage we begin from, we can still end there, because the cycle is like you are running a race in a football pitch, whereby the starting point, you're completing the cycle of the pitch. The starting point can still be the end point. So when we start here on the oxidized acetate itself is a 4 carbon molecule, a 4 carbon molecule, oxidized acetate, a 4 carbon molecule. So in the cycle, the acetyl enzyme A will find oxidized acetate in the cycle, and the cycle will just continue from there. So acetyl enzyme A, which is highly reactive with 2 carbon atoms, combines with oxidized acetate with 4 carbon atoms. It means that when you have 4 carbon atoms plus 2 carbon atoms, we are likely to form a 6 carbon atom, that is the citrate. That citrate there, in some sources, they will call it citric acid. Of course, we have just used the anions of the acids. So when you find people using oxaloacetic acid, malic acid, fumaric acid, succinic acid, alpha-ketoglutaric acid, they are 100% correct, as the earlier mentioned. So the citrate is a 6 carbon molecule, which is formed from oxaloacetate, and oxaloacetate with a combination with acetyl enzyme. So we form a citrate, which is a 6 carbon molecule. So from the citrate, you are going to have isomerization taking place. Isomerization taking place. Isomerization of the citrate to form isocitrate. Of course, when you look at part 1 of the Krebs cycle that I've earlier on taught you, I gave you details of how the cycle occurs, and now I'm giving you a summary. So I mentioned about isomerization of the citrate to the isocitrate. So after isomerization, now you may be wondering, what is the purpose of the isomerization? So when the structure changes from the citrate to isocitrate, again the reactivity may change. Its reactivity may change, or the stability may still change, because if you look at the citrate, is more stable than the isocitrate. So remember, the cycle needs molecules which are highly reactive. So the ones which are less reactive, they may not easily they may not be needed, because the cycle may not continue. So isocitrate is more unstable than the citrate. So the purpose of the isomerization is normally to increase the instability of that molecule. So isocitrate is more unstable than the citrate. So from the isocitrate, we are going to have decarboxylation followed by oxidation taking place at this stage. So stage number 3. So we're having oxidized NAD picking up a hydrogen from the isocitrate to form reduced NAD, and then we're having also decarboxylation taking place, whereby a single carbon dioxide molecule is lost to form alpha-ketoglutarate. So since we have lost a carbon, and then initially the isocitrate was having 6 carbons, so it means that if we lose 1 carbon through the carbon dioxide, so we're going to remain with a 5 carbon molecule, that is alpha-ketoglutarate. If someone says alpha-ketoglutaric acid, is also 100% correct. So at that stage, we are remaining with a 5 carbon molecule, that is alpha-ketoglutarate. We are having another, in step 4, we're having another successive decarboxylation. So this is the first decarboxylation, this is the second decarboxylation, whereby the 5 carbon molecule, the alpha-ketoglutarate, loses another carbon dioxide molecule. So there are 5 carbon atoms. Now, after losing a single molecule of carbon dioxide, we expect the number of carbon atoms to reduce from 5 to 4, like that. So from 5 to 4, we still have oxidation taking place, whereby NAD, which is oxidized, picks up a hydrogen and then to form reduced NAD, so that you can have oxidation of alpha-ketoglutarate to succinyl enzyme A. Of course, succinyl enzyme A is going to be having 4 carbon atoms. So where does the coenzyme A come from? Coenzyme A is going to be also added there. Coenzyme A is also going to be added there. But this coenzyme is readily available in the mitochondrial matrix, as you had earlier alone mentioned. So it is readily available. So what is its purpose? The succinyl alone is high. The stability of the succinyl is so high that for us to increase its instability, because we need molecules which are unstable for the reactivity to go on very well, the coenzyme A is going to get attached to the succinyl to make it highly unstable, so that the cycle can continue moving on. So the succinyl coenzyme A, which is a 4 carbon molecule, is going to get converted into a succinate. But what takes place is that there is going to be an addition of the inorganic phosphate, at that stage. Of course, as the inorganic phosphate is getting added, there is going to be replacement of the coenzyme A from the succinyl, so that the inorganic phosphate is added. So there is replacement again to make it more unstable. And then later on, this phosphate which has been added to the succinyl is going to get added to the GDP to form GTP. GDP is guanine diphosphate, and then GTP is guanine triphosphate. You may find out that in some organisms we shall find ADP being formed, receiving a phosphate molecule, and then producing ATP. So if I put here ATP, it is still okay. ATP and then ADP, it is still okay. So this phosphate molecule can displace the coenzyme A, and then we form succinyl phosphate, and then later on the phosphate is going to be released to GDP, so to form GTP at that stage. So energy is released at this stage. So ATP can be formed. If instead of using GTP, still you can use ATP, still is also okay. So after losing the phosphate molecule, it implies that even at this stage, the coenzyme A is going to turn back to the mitochondrial matrix, because the coenzyme is like maybe you can call it a catalyst. It is just helping in speeding up the rate of the reaction, and then it is going to get back like that. So coenzyme A is just readily available in the matrix, in the mitochondrial matrix. So the succinate is going to, from stage number 5 to stage number 6, the succinate is going to be converted to fumarate. At this stage, we are going to use FAD instead of NAD. FAD is going to help in oxidizing the succinate to fumarate. How does it oxidize it? It is going to remove 2 hydrogen atoms, and then we are going to form reduced FAD. Reduced FAD is the FAD which is having 2 hydrogen atoms. So oxidation of the succinate to fumarate at that stage. So from fumarate to malate, we're having addition of water molecule, and this stage is called hydration. The hydration stage, we are adding water. So after adding water, we are going to form malate. Sometimes you can call it malic acid, but we have used the anion, which is the malate. So stage number 7. So from stage number 7, we go to stage number 8, whereby the malate is getting back to the oxaloacetate, of which we are going to have oxidation of the malate to oxaloacetate. Of course, we are going to now this time use NAD, which is oxidized, to NAD, which is reduced. So hydrogen is picked up from the malate to form oxaloacetate. So we realize that the succinyl coenzyme A had 4 carbon atoms. Again, here we also still maintain, because we have not had any decarboxylation taking place from stage. The decarboxylation stopped from stage number 4. So stage number 5, 6, 7, 8, up to 8, there is no decarboxylation taking place. So decarboxylation normally takes place from stage number 3 to stage number 4, only the 2 stages. But now the remaining stages, we shall not have any decarboxylation taking place. So it implies that the remaining molecules are going to maintain the number of carbon atoms. So still, here we're having 4 carbon atoms, still 4 carbon atoms here in the malate, and then the oxaloacetate still 4 carbon atoms. So at the end of the day, we are going to look at the analysis of what we are getting from the cycle. So before we get into the cycle, that transition phase whereby we are activating our molecule that is going to enter into the cycle, there are some molecules which are produced at that stage. So we realize that in the transition stage, we don't have any energy that is being released at that stage. We don't have any energy being released, but we have other important molecules that are formed, which are later on going to be used in the cycle. For example, we are having NAD. So NAD H, that is reduced NAD, and when we count, we're only having one, but remember that we're having two pyruvate molecules. So each cycle, we said analysis per pyruvate. So per means one. So it means that if there are two, then it means you're going to multiply by what? By 2. So in the transition stage, we're having one NAD in each pyruvate molecule. So if there are two molecules, it means that you're going to have two reduced NAD. So one molecule of reduced NAD is being formed in one single pyruvate molecule. When there are two, so it means that you're going to have two molecules of reduced NAD. So you can look at carbon dioxide. It is only one still. You can just count it as only one carbon dioxide molecule being formed. So in the two pyruvate molecules, we shall form two. Acetyl coenzyme A, shall we form any acetyl coenzyme A? In fact, at that stage, acetyl coenzyme A is just added to the acetyl group. So it means that that one we shall not have it being formed at that stage. We shall not have acetyl coenzyme A being formed. So we have seen reduced NAD, we have seen carbon dioxide being formed at that stage. So what do we see later on? We can see that when we enter into the cycle, as we enter into the cycle, we can count how many NAD, how many FAD, reduced FAD, reduced NAD, GTP or ATP, and then carbon dioxide molecules formed. So let us start by looking at each stage. In stage 1, a coenzyme A is released. Of course, that one is going to be readily available within the mitochondrial matrix. We can look at the important molecules which have been formed from as a result of picking up molecules or picking up electrons from our molecules which are in the cycle. So the most important molecules we're having reduced NAD, reduced FAD, we're having energy, and then carbon dioxide. So in stage number 1, we don't have any reduced NAD, we don't have any reduced FAD, we don't have any energy, we don't have any carbon dioxide formed. So if we go to stage 2, the same case. Now in stage 3, we are having one reduced NAD being formed. We can begin by counting reduced NAD. So this is one reduced NAD being formed. So I can underline it, that one. We can go to stage 4. There is a second one. When we go to stage 5, we don't have any. Stage 6, we don't have any. Then stage 8, we're having reduced NAD. So making a total of 3 of them. So each pyruvate molecule gives us 3 reduced NAD molecules. We have just counted them and we have seen. So can go to reduced FAD. Reduced FAD, of course, we have only realized the FAD being formed in stage number 6, and it is only one. It is only one being formed in stage number 6. So it is only this in stage number 6. Then GTP or ATP, we have seen it being formed only once in stage number 5. So only once. So we need 2 molecules of the pyruvate. Of course, they are going to be 2. So carbon dioxide molecules, we can count them. We can see where decarboxylation took place. We are seeing in stage number 3, decarboxylation took place there, and then in stage number 4, a carboxylation took place there. So when you count the carbon dioxide molecules, we have 1, and then we're having 2. So we're having 2 of them. So in overall, we can say that for 2 pyruvate molecules to be for the 2 pyruvate molecules to enter into the cycle, actually, for the cycle to take place in the 2 pyruvate molecules, we shall have everything doubling here. We shall have everything doubling. So in total, we can have the NAD. So if we have 2 pyruvate molecules being used, so if we have 2 pyruvate molecules, when we add the NAD from the transition stage to the tricarboxylic acid cycle stage, we can count them that 1, 2, 3, 4. So NAD, produced NAD, we're going to have 4 times 2. The 2 is coming from the 2 pyruvate. So each pyruvate is going to produce 4 reduced NAD, giving us in total, giving us 8 NAD. So when you have FAD in the transition stage, the reduced FAD, the transition stage will not be there. So shall just only have 1 times what? 1 times 2, giving us a 2. Then GTP or ATP, we shall have 1 times 2, giving us only 2 ATP molecules from the 2 pyruvate molecules. Then carbon dioxide, we shall just have 2 molecules times 2 molecules. Of course, we know we shall get 4. So I have forgotten the carbon dioxide molecule which is produced in the transition stage. So it implies that there must be 3. There must be 3. So these 2 plus this one here. So 3 times 2, giving us 6 carbon dioxide molecules. So we have 6 carbon dioxide molecules produced, 2 reduced FAD molecules produced, and then 8 reduced NAD produced in the cycle. So some of those molecules are going to help us as you're entering into the electron transport chain. We are going to see reduced NAD, reduced FAD coming back and then being used. Like you can see that this reduced NAD, again, we obtained it as one of the products in the glycolysis and is now being used here. So even in the electron transport chain, it is going to be so useful. So that is the